In Chapter 4, we're going to continue looking at different groups of functions, namely exponential and logarithmic functions. Let's look at exponential functions first in Section 4.1. An exponential function, f of x, is defined as some base b raised to our variable x. Now, that base b has to be a real number, and it has to be positive. It has to be strictly greater than 0, and it cannot equal 1. And generically, exponential functions can be very good at modeling different processes. If your base b is larger than 1, it'll generically model a growth process. It will grow as the values of the variable x get larger. However, if b is fractional, it will model a process that looks like decay. So the value of the function will decrease as x gets larger. We're going to look up more closely at growth and decay models at the end of Chapter 4 in Section 4.5. In this section, we're going to have to use our calculators to evaluate exponential equations. Depending on the type of calculator you have, those steps can be different. If you have a graphing calculator, like the TI-84, usually you can just put the equation in directly and it will evaluate properly. If you're using a scientific calculator, the steps may have to be different. And very often with those calculators, you really need to follow the order of operations strictly to get the correct answers. Make sure you do practice with your calculator so you know how to use it and get the answers correctly for the problems in this section. Let's look at example 1 on page 465 of your textbook. And here we're going to work with an exponential model that models the dollars spent based on the amount of time spent in a mall. So always pay close attention to the details of any model. F of x, they tell us, is the dollars spent, and x is in hours. Those details can be important when working with application or modeling problems. So 4 hours, we're going to evaluate this function at the value of x equals 4. So here x is in our exponent, and there we'll have the value of 4. Now again, depending on the calculator you have, that can change how you evaluate it. Many calculators can evaluate this expression directly, but sometimes if you have a scientific calculator, following the order of operations can also be helpful. Remember that you would do an exponent here before multiplying by 42.2. So in some calculators, take your base of 1.56, raise it to the 4th power, and then multiply by 42.2. I'll illustrate these different methods with my built-in calculator. So one way I can do it is just directly. I can enter 42.2 times 1.56, and I can use the caret key to exponentiate that to 4, and we'll get $249.93, which will be rounded to $250, which is the final answer. I can also do it this way, 42.2 times, and then I can enter 1.56 and then use my x to the y button to also exponentiate and get the same answer. And if you have a scientific calculator and you need to do it slightly differently, again, you can do the exponent calculation first. So I can do 1.56, hit my x to the y button and get 4, and then multiply by 42.2. Again, notice we get the same answer each way. So just make sure you get some extra practice with your calculator so you know how to solve these problems correctly. And so we'll finish the problem with the answer of $250. Now, do pencil problem number 1. The next topic we will look at in our chapter is on graphing exponential functions. And when we graph exponential functions, the method we can use is very similar to what we've done with working with functions earlier in our transformations. We can create a table of coordinates with a minimum of 5 points, and we can select those typical x values from -2 to 2, substitute them into this function, and then graph our xy pairs from that table. Let's look at example 2 on page 466 of the text. So now f of x is 2 to the x. So we can select those 5 x values from -2 to 2 and substitute them into the function. Now, don't forget your rules of exponents. 2 to the -2, remember, a negative exponent is 1 over that expression with the positive exponent. So this would be 1 over 2 squared, or 1/4. f of minus 1, that would be 2 to the minus 1 power, or 1 over 2 to the first power, which is 1/2. F of 0 is 2 to the 0. Remember, anything to the 0 power will be 1. And then f of 1 is just 2 to the first, or 2. And f of 2 will be 2 squared, which is 4. And now that we have our coordinate points, we can graph. So we'll have this point at minus 2 and 1/4. The fractional value we can plot approximately. At minus 1, we're at 1/2. X is 0, we're at 1. At 1, we're at 2. And then at 2, we're at 4. So there are our coordinate points. And the graph will look approximately like this. Exponential functions do have a horizontal asymptote at y equals 0. So this graph technically will never touch the x-axis. So I've drawn in that asymptote here, and the domain of this exponential function is all real numbers, right? Minus infinity to infinity, and the range is 0 to infinity. Notice the parenthesis next to 0. It's not a bracket because of this asymptotic behavior. The graph will never touch the value of x equals 0. So we must have a parenthesis here. Now do pencil problems 2a and 2b. And for each of those problems, make a table of coordinates using these 5 x values to plot. Example 3 on page 466 of your textbook asks us to graph another exponential function, g of x equals 1/2 to the x power. Now notice this base is fractional, so this will really model a decay process. Now, there are a few different ways to look at calculating the table of coordinates. Your text will show that 1/2 we can write as 2 to the minus 1 power, and then we can rewrite the expression g of x as 2 to the minus x. We can rewrite the function in that form. So then when we start to substitute our x values in, well, when x is minus 2, 2 to the minus 2 power will be 2 squared, or 4. You can also work with the original base, 1/2, but just realize that this negative exponent is really going to flip this whole fraction over. So 2 squared is 4, we'll get the same answer. So similarly, we evaluate when x is minus 1. Again, 1/2 to the minus 1 power will really be 1 over 1/2, which will evaluate to 2. That fraction will flip over. However, if you use the rewritten form as the text shows, minus 1 would be a plus 1. You'll still get the same answer. 2 to the first power is 2. And as always, when x is 0, the function will be 1. And then when we have 1/2 to the first power, that's really just 1/2. And 1/2 squared will really just be 1/4. Now that we have our coordinate points, let's graph the function. So when x is minus 2, we'll be at plus 4. When x is minus 1, we'll be at plus 2. When x is 0, we're at 1. And again, we'll have these fractional values. When x is 1, this point will be 1/2. And when x is 2, we'll be at 1/4. And so the graph will look approximately like this. To complete the picture, I will add that horizontal asymptote at y equals 0. And notice the domain and range are actually the same as we saw in example 2. Domain is all real numbers, and the range is still 0 to infinity. Again, note the parenthesis. It's not a bracket because the graph will never touch the x-axis and have the value of x equals 0. Now that we've learned how to graph exponential functions, we'll look at transformations of those functions. And for our purposes, for exponential functions, we'll only focus on horizontal and vertical shifts. So let's look at example 4 on page 469 of your textbook. Here they want us to use the graph of f of x equals 3 to the x power to graph g of x, which is 3 to the x plus 1 power. Now remember, with your transformations, we can always identify a vertical transformation because it's outside the argument of the function, or a horizontal transformation when it's on the inside of the argument of the function. Because this plus 1 is up here with the x variable, it's really a horizontal shift, and it's going to be a shift left 1 unit. Just as we did in Chapter 2, you want to identify any transformations you have and what order you may have to do them in. So here we have a horizontal shift left 1 unit. We're going to subtract 1 from the x coordinates. First, we need to come up with a table of coordinates for f of x, and then we can apply the transformation to graph the final function. So again, we'll pick our 5x values from -2 to 2, and then 3 to the -2 power. That'll be 1 over 3 squared. That will be 1/9. 3 to the -1 power. That'll be really 1 over 3 to the first power, or 1/3. 3 to the 0 power will be 1, and then of course 3 to the first is 3, and 3 squared is 9. So now we can apply our transformation. So we'll create that second table of coordinates for g of x. Now again, notice this is a horizontal shift, so we're not going to change the y values, so I'll just copy those over. And now I just want to subtract 1 from the x coordinates. So we'll have -3, -2, -1, 0, and 1. Now that we have our final table of coordinates, we can plot the points. So we'll be at -3 and 1/9, about here, -2 and 1/3, right about there. Then -1 and 1 will be here, 0 and 3 will be here, and 1/9 would be off the scale a bit here, but of course we can plot it approximately. And so then we can complete the curve. And we do still have our horizontal asymptote at y equals 0. Let's look at example 5 on page 469 of your textbook. Now they want us to use the graph of f of x equals 2 to the x power to graph g of x equals 2 to the x minus 3. Now notice this minus 3 is outside the argument of the function. It's not up here with the exponent of x. So that's how we know it's a vertical shift. So as we've done in our other problems, we want to identify what the transformation is. So that's a vertical shift down 3 units. And of course, now we will subtract 3 from the y coordinates. Just as we did in our previous examples, we'll generate a table of coordinates with 5 points for f of x, using our x values from -2 to 2. So we'll get 1/4, 1/2, 1, 2, and 4. And now let's apply the transformation. So again, this is a vertical shift down. We're going to subtract 3 from the y coordinates. So we can copy the x values down. We're not going to change them. So I'll just copy -2, -1, 0, 1, and 2. And now let's subtract 3 from our y coordinates. Now there's a little fractional math here. So remember, 3 in fourths is 12 fourths. So 1/4 minus 12 fourths, that'll be minus 11 fourths, right? 1/2, well, 3 in halves would be 6 halves. So 1/2 minus 6 halves is a minus 5 halves. And then 1 minus 3 is -2. 2 minus 3 is -1. And 4 minus 3 would be 1. Now let's graph the points of the transform function. So when x is -2, we're at -11 fourths, which is -2 3/4 in mixed number format. So I'll go down to about here, be about -2 3/4. Right? When x is -1, we're at -2 1/2 in mixed number format, or -5 halves. I'll be about here. And then at 0, we're at -2. And then 1, we're at -1. And then when x is 2, we're at 1. Then we'll complete the graph. And it will look something like this. One thing that's important to note in this example is that your horizontal asymptote from y equals 0 with a vertical shift will also shift. So notice, because we shifted down 3 units vertically, that now the horizontal asymptote is at -3 and not 0. So that's one important thing from this example. Your horizontal asymptotes can shift with transformation problems. Now do pencil problems 2C and 2D.